We're going to switch gears again. Many of you may not have liked math in school very much, and that's where Jason Harron comes in. Jason is from the Bagwell College of Education, School of Instructional Technology and Innovation, and we'll be talking about making math visible, rediscovering your curiosity.
Have you ever wondered why math can sometimes feel so confusing, yet so awe-inspiring? Think back to middle school math. At that time, everything was shapes and numbers, and then all of a sudden one day your teacher introduced you to algebra, and it all became solve for x. And at some point, you were introduced to the Pythagorean theorem. Now, some teachers like to teach about Pythagorean theorem by telling stories. So I would tell how sailors used to wrap a rope around their forearm 3, 4, 5 times to make a perfect Pythagorean triple in order to make perfect right angles for their sail and also to make stable boats. I might reach for a bucket of blocks or Lego pieces, and we might do hands-on activities to see the 3 times 3 and 4 times 4 equals 5 times 5 that we see up here on the screen. This brings us to our central question of the presentation. How can we foster an appreciation for the wonder, the joy, and the beauty of mathematics? If we look around us in the world, math is everywhere. We see it in nebulas, we see it in tessellating tiles, we see it in nautilus shells. Take, for example, if you look outside here in Atlanta, Georgia, you can stare up at the trees and you can see the phenomenon known as crown shyness. If you look at this, this is a natural pattern that's kind of puzzle-like that emerges between the crown of the trees. They brush against each other. Well, the next time you get some honey, take a look at the honeycomb. The honeycomb also features a shape that we call a Voronoi pattern. We can find that in the pattern that is in the body of a giraffe. And tomorrow night, when you're doing your dishes, look down to the sink and you'll find it in your soap bubbles in 3 dimensions. We can also find it in very delicate structures, such as the wing of a dragonfly, and also up in that tree canopy in the cells of the leaves. We can take inspiration from these patterns when we're looking at designs, looking at art, and looking at architecture in the world. Take, for example, prosthetics. Prosthetics can use these Voronoi patterns to make shapes that are natural, strong, light, and durable. They also apply to furniture and architecture, where we can get these sleek, natural, aesthetic lines. But ultimately, math is not frequently taught this way. Math is often taught about in the textbooks as abstract number and symbol manipulation. So that begs the question, how can we make math more approachable so we don't tune people out early in life so they start hating math? So in my research, I work with advanced manufacturing technologies such as 3D printers, laser cutters, and computer-aided design to teach K through 12 teachers and students how to actually create their own math manipulatives. If we take a look up here, we got this little nautilus gear, that inspiration that we saw earlier on the slide. And also in a moment, we're going to see here a simple little tool that's for teaching Pythagorean theorem. So going back to the earlier example, Pythagorean theorem is often taught by teachers by putting down some letters and numbers and calculating it out a bunch of times. This tool can be made for about $2. It has a 3D printed top and bottom, and then a laser cut acrylic sheet that goes in the middle that shows the subdivision of each one of the blocks. We can fill it up with some tiny little beads. So in this case, I have some glass beads that are actually from the 1980s that were used for bedazzling. I found a deal on it on eBay. But you can tilt it over, and you can see that visual representation that a squared plus b squared does indeed equal c squared. Now, we can take this exact same concept and apply it to statistics. So this tool here is called a Galton board. I worked with a high school intern from Wheeler High School, and she went together and we put together this shape. And what it does is when you flip it over, about 3,000 ball bearings fall. It's like a really fast Plinko game, essentially. And it can show you standard deviation. You can tilt it a little bit to the left if you want a left skew. You can tilt it a little bit to the right. But once again, it's another great visual demonstration. But not everybody has access to these advanced technologies for printing these. So I can take that exact 3D model, I can throw it into like kind of a game engine, throw some physics on it, and now I can do a virtual simulation using all of the exact same tools. Now, if we think about other ways that this can be applied, you ever stop and think to yourself, hey, how did those N95 masks actually work? Well, we can talk about scale factor. Nanofibers are inside of those masks, and they're really, really, really tiny. Well, I can go ahead and make a model in simulation, and I can actually simulate what is going on inside that N95 mask. In this example, the fibers in the middle are about 17 nanometers. The red dots on the right are about 100 nanometers, and the one on the left is about 300 nanometers. We can see the red ones are kind of bouncing around because they're experiencing Brownian motion, but this shows how mechanical and electrostatic separation can take place within one of those masks. Or I could take my classroom, for example, and using like a VR headset, I could scan my classroom and we could find out about polygons, like all those triangles up there. We could calculate the volume of that classroom, or I could just be silly and shoot balls at my dog Tater Tot if I want to. But this leaves an opportunity to talk about things such as angles of reflection, and I can actually turn the gravity off on this, and it becomes a gas diffusion simulator for the science classroom. So, as we've seen in this brief presentation, there's a lot of different ways that we can approach how we teach mathematics in the classroom. Hands-on models and virtual simulations offer another avenue to make math more relatable for teachers and students. So this brings us back to the central question of this presentation. How do we make math how do we foster an appreciation for the wonder, the joy, and the beauty of mathematics in our everyday life? I believe that hands-on mathematics and seeing it in nature is one of the ways that we can make math more relatable for all teachers and all students. When I run workshops, I often ask my teachers to send me pictures about what they see after they've come to the workshop. The one on the left is that now familiar Verone pattern in a mint leaf that they found in the yard. But the one on the right was an Easter orchid. And if you look at it, it has one petal, then two, then three, then five. That's the Fibonacci sequence there in nature for us to discover once we understand the mathematics. So, ultimately, if we want to foster an appreciation for mathematics, we need to engage in exploration, play, and discovery. Ultimately, to foster an appreciation for the wonder, beauty, and joy of mathematics, we need to look into nature and find its endless possibilities.